I am pleased to introduce our speaker for today, Dr. John Barclay. He received his PhD right here at Berkeley in physical chemistry, and he went on to do a wide variety of things in alternative energy. So currently, he is a managing member and a CTO of Emerald Energy Northwest, and he has 125 publications and 15 patents to his name, and he's won numerous awards. He was also previously the CTO of Prometheus Energy Group, which is currently up for a major award. And he was the founder of Cryofuel Systems, all in the Seattle area. He previously was a professor at the University of Victoria, British Columbia, and he led the Advanced Technology Group at Astronautics Corporation of America. And Dr. Barclay may not realize it, but he actually was a household name at my house growing up for a number of years. My father worked for him back when my father was about my age at Astronautics. And so when we were coming up with speakers to invite, I immediately thought of Dr. Barclay for that reason. And also when I chose Berkeley, my father immediately told me, oh, well, Dr. Barclay, he went there. Okay. With that, I am pleased to introduce Dr. Barclay, and please join me in welcoming him.
Thank you, Amber. Her father was one of my most creative design engineers. So, I'm going to try an experiment here. This is an opportunity to sort of transmit some experiences that I've had over a very enjoyable career. And it's a wonderful statistical thing, problem that you do, the drunken sailor walk, okay, that problem. And my career seems to be a little bit like that. It seems to go lots of different places. But those all were related to something that I was interested in doing, which was related to advanced energy systems and research associated with that. So I'm going to go through this talk. I'm happy to answer questions depending on how you do it, but I think it's probably better to walk through this and then ask questions at the end. But that's totally, however your format is, I'm totally comfortable with either one of those. Okay. So let's start, and I will first of all say thank you so much. It's a great honor to be back. I did actually leave here in 1969 with a PhD in hand, and 2 weeks later I was in Australia, and I was on a fellowship there, and that's the beginning of a path. But to come here in 1964 when Mario Savio was down on Frau Hall steps speaking about free speech, and having come from University of Notre Dame, which is probably one of the more conservative universities in the country, to Berkeley, which was one of the more liberal universities in the country, it was a very interesting experience. And part of the reason that I believe I am a reasonably objective, open-minded scientist is because it's forced upon you, okay, when you come to the University of California, Berkeley. And so, anyway, let me start. I've got a series of lessons that I'd like to share with you. The first one is that there are about 5 billion people in the globe that would like to live like about 500 million of us do. And that is a huge thing that's happening. And you may have heard the acronym BRIC: Brazil, Russia, India, and China. Those are major players in this process. And they are going to really change how our whole world is in the next 20, 30 years. The key issues are food, water, energy, and energy is really key in this. Energy per capita is strongly coupled to the economy. You see plots of energy per capita function of GDP. Its price of energy is a major variable in how the economy evolves. And you only have to look at the price of fuel at the pump $4.25 for gasoline or more for diesel, to know that it impacts you directly. So it's important, and it's important over the globe. Energy is also strongly coupled to the environment. It's critical that if we just go ahead and do business as usual, for example, to say we're going to provide all the energy that these countries that are changing, going from third world to first world countries, we will choke on CO2 because it's going to be coming from high carbon fuels. So climate, and Sandy is a good example, one of the largest storms that occurred today. Well, greenhouse gases, air quality, California is way up the curve on these two. I'll show you a project later on that we did in the South Coast Air Quality Management District in Southern California, and it's one of the toughest places in the world to get a permit to do something related to the environment. So these are all related, and they're really, really important. Finally, what I want to leave you with is it's important to understand and improve energy systems. You don't take anything else away from that. Make sure you understand that, because it's going to be a really critical thing. Lesson 2, understand the heat trap. I'm going back to beginning, okay? After I left here, I took an Australian Institute of Nuclear Science and Engineering postdoc at Monash University in Melbourne, Georgia. About 15,000 students. It was a relatively modern university, but very good. One of the top, say, 10 or so universities in Australia. And eventually, I finished that 2-year postdoc and got offered a position as a chemistry graduate in the physics department. So that was always a little bit interesting. And one of the things that 3 of us did in the young lecturers was to develop a new course called Physical Science for Non-Scientists. So we were trying to say, how do we reach out to the other people at the University at Monash and introduce them to energy systems? And that's actually quite an interesting question to answer and address. And what we tried to figure out, what topics would we teach? How do you teach somebody that's had maybe general science at freshman year in high school and no science beyond that? How do you teach them what the concept of temperature is? How do you teach them what energy is? How do you teach them what all kinds of other things are when you're trying to describe energy systems? And of course, one of the things that we were looking at is how the different forms of energy was one of the topics. So we talked about chemical potential, nuclear, gravitational, and we did the calculations, for example, of how much nuclear waste would be involved for producing all the global energy using nuclear. And got some staggering numbers, and so that sort of opened some of their eyes. We did chemical potential and looked at that, and a lot of good examples, gravitation, and so on. And the students sort of got this idea. The thing that got me was interesting that we can do energy conversion. First of all, they always thought energy is used. So teaching concept of conservation of energy was something new. And that was interesting. We did that. And you convert from one form to another. And most of these are semi-reversible. But most of them also have some aspect of that conversion that turns up to be thermal energy. And so you go to all these different lists, and you can go to just about anything you can think of, converting one form of energy to another form of energy, and you end up with thermal. And once you get to thermal energy, the key point that I learned way back then is you can't get it all back. Okay, so you're locked into this heat trap, and that to me said to me, my golly, I better really start to study thermodynamics. And I begin to do that and seriously trying to understand how you manipulate thermal energy to the maximum possible efficiency. And so the heat trap is a very important thing to understand, in my opinion, and the applied thermodynamics is, of course, incredibly important to chemical engineering, and so it's important to do that. Third lesson, choose relevant topic projects. And this, after 8 years in Australia, I was on a speaking tour going around the world. Australia is a long ways away, and I wanted to continue to interact with my colleagues, and I was on a speaking tour, and ended up giving a talk at Los Alamos National Lab. And it wasn't too long after that they said, my God, we've got a perfect job for you. Would you like to apply for this? And I said, wow. And I said, yes. It was in the energy division, so it's outside defense, as they say, so I wasn't working on weapons. I was working energy systems, and they wanted to work on this particular condensed matter and thermal physics group. They were working on cryogenic engineering, low temperature physics, and that just fit perfectly with what I've been working on at Los Alamos. By the way, my PhD was done up at the Rad Lab with David Shirley, and we were doing work at about between 5 and 10 millikelvin, looking at a whole bunch of interesting, neat things that happen when you cool samples down to those low temperatures. So, and he had done his PhD with Professor Joke. And when I came to these seminars over in the chemistry department, occasionally Professor Joke would come in and sit down about right there where that blue sweater is, white hair, retired already, and he would, at the end of the seminar, ask 3 or 4 incredibly penetrating questions. So you can try that on me. You may not get the same kind of answers as he expected to get.
I'll leave that to Dr. President.
Okay, there you go. So basically, Los Alamos is research heaven. It's a place you go when you want to learn an immense number of new things. And I learned all kinds of thermal physics. I learned how to do very elegant computational fluid dynamics. I learned how to do materials work, all kinds of things. And anything you don't know, about 3 phone calls, and you find somebody that knows the answer. And that's why I call it research heaven. And you had a lot of money, so that was very nice. And I was recruited for applied superconductivity projects, and so I began to explore efficient magnetic refrigeration. And this was something where obviously I knew about magnetic refrigeration because I had gone down to 5 or 10 millikelvin using magnetic refrigeration, but it was from 1 Kelvin down to 5 millikelvin, not upwards. And that's the classic magnetic demagnetization, adiabatic magnetization that you do. Well, a colleague, Jerry Brown at NASA Lewis in Cleveland, had done something really quite remarkable. He had taken gadolinium metal, it's a ferromagnet, at room temperature. It has a Curie temperature just about 300 Kelvin, and he had turned it into thin sheets, put it into a magnetic field, and its temperature increased to 7 Tesla magnetic field. Temperature went up by about 15 degrees. And then he put it through, he moved actually a column of alcohol, and cooled the magnetic material down by this column of alcohol, which had a temperature gradient in it, and then demagnetized it. It cooled the bottom of the column of alcohol, and he moved this column of alcohol back and forth when he magnetized it, demagnetized the thing. And amazingly enough, with the 15-degree temperature change, he got a span in this alcohol column of about 80 degrees Kelvin at room temperature, and it blew me away. I couldn't imagine that you could do that with magnetic refrigeration. So we began to look at that seriously, and started at 1 Kelvin and going upwards in temperature, up towards 300 Kelvin was what we were doing at Los Alamos. Very interesting problem, and this was very interesting because when we did the calculations, it looked like magnetic refrigeration had the possibility of being very efficient, which was what I was trying to accomplish. Anyway, we were working on a project from BOE. It's a 1 gigawatt superconducting power transmission line. Interesting enough, they call this SPTA SPIL. Interesting names for things, but it required many kilowatts of cooling to 5 Kelvin with supercritical helium. And this is a big refrigeration project. We were asked to work on this, and one of the problems that I had to solve was how long does it take to cool down a superconducting power transmission line that's 100 kilometers long. And this is a cable about this big around, a superconductor in the middle. Got all these 19 layers of stuff that you do to isolate it thermally, and then you put supercritical helium down the center and cool it down to 5 Kelvin. Superconducting, you can carry a huge amount of power in it. That was what the problem was. And it was very interesting. It takes about 2 weeks, by the way, to calculate. That's how long it takes to cool that down. You can do that calculation. It's very interesting. But what I found as I was doing this problem after about a year of working on this kind of thing, I then began to look at what matters. And I said, if I take the efficiency of this helium refrigerator and magically turn it into a very efficient, 100% efficient refrigerator, what happens? And the answer was nothing. Okay? And so I found myself frustrated because I had a problem where all the work I was doing didn't have any impact on the problem. And so the real problem was all the engineering goes into it, all the superconducting stuff, the refrigeration was very, very low impact. And so I said, my God, I want to work on something that has an impact. I began to look at where could I apply more efficient magnetic refrigeration, and about that time, there were two places that came up. One was liquid hydrogen, and one was space. And so the liquid hydrogen one actually was very interesting when it came from Kennedy Space Center. They came out and talked to us about the launch pad 39A and B, which are those big launch pads where the shuttles actually took off from. And we went out, visited there, and 875,000 gallon barrel of liquid hydrogen, great big huge barrel filled with liquid hydrogen. The boil off from that tank would cost NASA about $6 million a year. The boil off would come off, they put it out to a burn pond, and you see all these little things pop up on this water, about a block of water, and they would burn. And that's how they got rid of the hydrogen. They burned it off. They said, can you design a refrigerator that will re-liquefy that boil-off hydrogen and make it efficient, make it cost-effective and small? And so that was the first one of these things that was associated with liquid hydrogen. The other one that was interesting was Lockheed came to us, and many of you have probably heard of Lockheed Skunk Works, where they developed some of the really advanced planes in the world. Well, they had a design from Lockheed Skunk Works that wanted to fly a plane fueled on liquid hydrogen, and they wanted to stay up for 24 hours straight. And so, well, yeah, can you do something like that? I said, well, yeah, we probably can. And of course, you always say yes when somebody comes in with a question like that. And so we did, and we began to look at it, and that then was interesting enough for them to say, now, can you build a liquid hydrogen plant that would satisfy all the airplanes that came into San Francisco International? And Chicago O'Hare was the other one they had to look at. And wow, that turns out to be a lot of liquid hydrogen that fueled all the planes that were coming in. So we did that study for Lockheed, and that said, wow, this is a problem where this matters. Liquid hydrogen is a very fragile cryogen. Vaporizes quite easily. It has a very low, almost as bad as helium, but it has a very low latent heat and a very high sensible heat. So you look at it and it evaporates almost. Okay, so you have to really insulate it well, and you have to liquefy it at 20 Kelvin, and that takes a lot of energy. So efficiency mattered a lot, and there was a lot of it that was important. The other thing that we realized was that in space there was an application as well, where they were looking at cryocoolers on a cooling a sensor in space application, where they're looking down 40 miles up, and the signal to noise is a big issue. So you have to cool it down to around 4 Kelvin to reduce the signal to noise to low enough to be able to read the paper on your desk, okay, from that distance up. But they can do that kind of thing. And so they were asking us, and this came from DARPA, you know DARPA, and it also came from some of the Air Force, Wright-Patterson Air Force Base, asking us, could you design an efficient small refrigerator that could go into space? And it turns out that we thought we could begin to look at that. So these are the things that I got involved in as a result of being frustrated by this project here. I finished that project up and moved on to other things. So lesson 3, choose projects you're really turned on by and they make a difference. All right, that's what I would say to you. This is a really interesting one. These are called the Strobridge curves. How many people have seen these before? But Dick Strobridge was from, at the time, at National Bureau of Standards at Boulder, NIST now, at Boulder. And what he did was to collect a whole bunch of data from existing or under development refrigerators and liquefiers. Because what I wanted to understand was why the liquefiers for hydrogen were as inefficient as they looked like they were. And so I've got this curve, and a couple things that jump out at you. Look at this curve. This is percent of Carnot. So it's normalized to Carnot efficiency. It clearly takes, 74 watts per watt to cool something from helium temperature 4 degrees Kelvin to 300 Kelvin. Okay? Carnot factor is T hot over T cold minus 1. Okay? That factor is 74 for helium. It's 14 for hydrogen. So it means that for every watt of cooling power that you put in at low temperatures, you have to put in 74 or 14. And if that's what this means relative to Carnot. So you normalize it that way. But what he put on this plot, there's a lot of data points here, and you notice that about 30, this is 10%, 20%, 30%, the highest efficiency that any of these devices had was about 32, 35%. And this is a megawatt of cooling power. So this is a cooling power. Your little cryo coolers are in this sort of range over here. They're a few percent. So if you want to make a helium refrigerator work down here at 1 watt, you're probably going to pay about 7.5 kilowatts for every watt of refrigeration. And if those of you that use a Giff McMahon cryo cooler in any of your experiments, you'll see that that's about the size of the compressor that you have. So that's real. Now, what's interesting, first of all, it goes to 35. And the second thing that was really more interesting to me was that this is temperature dependent. So you sort of intuitively, I say, well, it's got to be much more difficult to make a helium liquefier or a hydrogen liquefier than a liquid nitrogen liquefier. Not true. Okay? And so you say, what does that mean? Okay? And you think about it, ask the question, again, understand the implications of the data. The lesson that I took from this, it meant what? It meant that the inefficiency was already gone before you ever got to the cold temperature. You already had blown it. And sure enough, when you then begin to think about what could that be, it's a compressor. Okay? So here's good old thermodynamics, control volume around. Beautiful thing about thermodynamics, you can draw the control volume where you want to. So you take it around the compressor, work in, mass flow through it, feed out potentially, low pressure in, high pressure out, and you apply first law of thermodynamics, basically the open law for open systems, right here to this system, and you end up with an isotropic compressor. That Q is 0, entropy doesn't change, it's constant, and hence you end up with this relatively straightforward expression for the work per unit mass, work rate per unit mass flow of the difference in enthalpies at high and low pressures. If you do it isothermally, you get a more complicated expression because you now have heat transfer out of the system, and you get something that involves the entropy changes and the enthalpy. Pretty important equation in liquefaction. So analyzing this, it shows, better look over here. If you do an iso, this is the temperature entry diagram. Again, you all know these very well, I'm sure. Low pressures and high pressures. In fact, these are reversed. This should be low pressure, this should be high pressure. And you start from this pressure here, you go up isotropically, and lo and behold, the temperature jumps up. That's no problem. I'll just put a good aftercooler after the compression. I'll get all that energy back. If you do a polytropic compression and then the isothermal compression, this is the minimum work you can put in for a compressor, and that's the ideal compressor. Perfect compressor is an isothermal compression process. So you take that and you say, my gosh, clearly this is huge. Now, the killer is that as soon as you take that up to high temperatures, it's inefficient. You can never capture all that energy efficiently. You create entropy because you're transferring heat across the delta T. And I'll show you that in just a minute. So, sure enough, and this temperature, by the way, is not particularly small. It depends on the gas you're compressing, gamma of the gas, but also the pressure ratio. But this could be 200 or 300 Kelvin, so it's a significant temperature change. So, that's where we found that. We then did, and I'll show you in one more corroborating thing. This is what we actually do, process flow diagrams for these kinds of things. But here is a hydrogen liquefier. Don't worry about this. Is the liquid nitrogen loop. But if you take and look at this process flow, it's pre-cooled in this heat exchanger. Further in liquid nitrogen goes down through this heat exchanger. It's split here. Part of it goes through the expander to provide cooling. This is an isentropic expander, which is the perfect one. Goes back here, comes back through, provides cooling for the other part of the process stream, which goes on down, and eventually goes through a JT valve. So the characteristic of a quad cycle liquefier is a combination of an isentropic expander and an isenthalpic expander, which is the JT valve. And you get some yield with liquid hydrogen, the gas comes back and goes through this whole system. Now, so you can take and draw these up and analyze these. You can use HYSIS or a number of other good codes to analyze these in great detail. What you'll find is if you go back and look at the literature, there was a very good scientist, Charlie Baker, at Pratt Air, a very reliable cryogenic engineering. He looked at the quantitative thermodynamic analysis of the pre-cooled quad cycle for hydrogen. And here it is. 225 metric tons per day. That's about just less than 1 million gallons per day. So it's a pretty big liquefier. So all the efficiencies are going to be in that system. And he went and calculated this in Journal of Hydrogen Energy. You can look it up. Ideal work of liquefaction is this number here in kilowatt hours per kilogram, or this in kilojoules per kilogram. And the real work of liquefaction is, and I'll show you how that relates in a minute, but it's several times higher, 3 times higher. The figure of merit, how measure of the performance of a liquefier, is 0.36. That's about as good as you can get. And so the detailed analysis identified here, the work increases and the efficiency reduced. You look at all the different things that he did, and lo and behold, sure enough, all 3 of those compressors produce over 60% of your work. And so you had the culprit of what we needed. So the next thing that we did, we learned, I remember specifically learning from, was to take, and normally you take the second law of thermodynamics and you say it's an inequality. The total entropy of a process is greater than or equal to something. And Tolman and Fine, and Tolman is the statistical mechanics author, some of you have used his book, Reviews of Modern Physics about 1948, they decided to write this the second law of thermodynamics as an equality here. So the work total is, take the second part of this, the cooling power times the Carnot factor, plus the integral over the irreversible entropy produced in a cycle normalized over that same temperature range. And this was, I thought it was a stunning thing, because now it meant that if I had this equations for the irreversible entropy production, I could get a detailed understanding of the efficiency of all these different cycles. And that's precisely what I proceeded to start to do for magnetic cycles, in addition to gas cycles. And the figure of merit, as I mentioned before, is a ratio of the ideal minimum work, that's the best you can do for a particular gas, divided by the real work. Okay? So here's another lesson. It's really important to get this and understand the second law of thermodynamics for analyzing systems and understand irreversible entropy. Here's an example to show you how important that is. Let's assume that I have a refrigerator that has got a heat exchanger that cools the heat exchanger to say 20 Kelvin, and I'm putting purified gaseous hydrogen at 300 Kelvin, a tenth of a megapascal, through that heat exchanger and making liquid. All right? And I calculate how much work I have to put into this refrigerator to provide the cooling power. And you can calculate the cooling power required is the enthalpy difference for this stream from this point to this point, well-defined. You can look up for that hydrogen, take a certain unit mass and calculate that. That gives you the cooling power of this heat exchanger. So this cooling power goes into this refrigerator. The work comes in to pump that heat up to high temperature, and you can calculate all these things very nicely. When you do this calculation with the perfect refrigerator and a perfect heat exchanger, it's 100% perfect, both of those. The figure of merit that you get for this, 25%. Where did that happen? Okay. And of course, if you think about it a little bit, it's right here. It's in the approach. So at the top end of this heat exchanger, you've got 300 K gas looking at 20 degrees K. So you've got that temperature approach. It collapses very fast. That temperature approach collapses in that heat exchanger because it's a perfect heat exchanger. But you have created entropy like you wouldn't believe in that process. And so what it tells you is that even with perfect components, if you don't design the system such that temperature approaches are small, you will never get an efficient device. So there's 2 things we came out with. 1, we have to eliminate the compressor. Number 2, we have to have very small temperature approaches throughout our design. Otherwise, we can't get it a really, really efficient device. So we began to explore magnetic, and again, most of you probably see this, I'll go quickly through this. Here's a conventional compression of gas that heats up. You can take that heat out, expand the gas. After you do that, it cools, and you can add heat. So this is a gas Carnot cycle, pretty standard type of device. This temperature changes can be 100 degrees Kelvin or more in the conventional device, depending on the gas and the compression ratio. The magnetic analogy is that if you take a magnet here, and you take a magnetic material like gadolinium metal, or you got probably 300 of these materials that you could use. You put it into a magnetic field that heats up. Gadolinium heats up by about 2 degrees per Tesla. So if we have a 7 Tesla magnetic field, you get about 15 degrees. So it's less than this 100 degrees or so here in this process, which is important if you want to keep the temperature small. You then take heat out, then pull it out, and it cools down. This can then add heat to it. So this is a magnetic Carnot cycle. This cycle, though, only goes about 15 degrees max, and that doesn't get you from 300 Kelvin to 20 Kelvin, which is what we wanted to accomplish. So you have to take another step. You have to say, aha, how do I get a large temperature span? And you design a refrigerator that has the following steps in it. It has an adiabatic magnetization process. This is where we put it into the field. Here's the high field region. And we then take the heat of magnetization away, the heat exchanger. And then before we take it out of the magnetic field, we run it through a regenerator. This is a Jerry Brown thing where you put it through that alcohol column. And that's what he used to do that. He cooled it down before he demagnetized it. We then pick up a load, put it back through the regenerator, and we have a complete cycle. So this regenerator, because it has a T hot at one end and a T cold at the other end, increases the span of the refrigerator. And if you have a really efficient regenerator here, you can increase the span arbitrarily. So regenerator, you know what a regenerator is? It's a periodic heat exchanger. Okay? So it's more complex than the steady state counterflow heat exchanger. So you have to understand this device, and it's periodic, but it's time dependent, goes back and forth. The flow goes back and forth to the regenerator. In one of the Mock Jaffa books that I first learned about this, he said this is one of the most complex thermal devices known to man. And so I take him at his word. I'm still trying to figure the damn thing out. Okay. So the next lesson is capture IP. Well, I don't know how many of you have thought about something that you think, my God, I've got something that's really unique and new. Novel, useful, and what else? 3 things you have to satisfy. Useful, novel, and something I'll think of it in a minute. Anyway, intellectual property, IP. So if you have new ideas, and I'm sure the University of California, Berkeley has a process for doing that and dealing with that, but once you get into industry or other jobs, it's going to be critically important for you. So what we did at Los Alamos is before we could publish a paper at Los Alamos, we had to submit it through the intellectual property division. They had to test you on it. So, and if it was new IP, you had to apply for a patent before you could release it to the press. So here's a case where Bill Steyer and I came up with the idea of combining the refrigerant and the regenerator to make a new cycle called the active magnetic regenerative cycle. This is the way it works. This is a regenerator, just a layered bed from right to left. This is up near room temperature, and then we layer different materials. There might be 10 materials in this, all the way down to some cold temperature that we want to reach. So we just select different materials with different current points, different adiabatic temperature changes, and you put that together in a device like this, and then you magnetize it. If you do that, the whole thing goes up in temperature by some delta T, which is proportional to temperature, and then you flow gas from the left side to the right side, taking that heat of magnetization away for the whole thing. Now demagnetize it. Once you blow to a certain extent, it cools down, and now you take this gas that you put through a heat exchanger and you put it back through, go the other way, you get cold gas, you can pick up a load. And here's the cycle. So this is a TS diagram for magnetic material. We increase the magnetic field, and adiabatic, in this case, you see, goes up to by some delta T. We then run the fluid through it to cool it. We then demagnetize. We come back up by reversing the flow of the gas. So this little cycle here is a magnetic braking cycle. And when you couple a whole bunch of magnetic braking cycles together like this with the heat transfer fluid, you get the active magnetic cycle. It was new. We got a patent on it. By the way, it just expired not too long ago. But that was it got a lot of publicity because people begin to look at a cycle like this that could do that. Now, next lesson, entropy change. And I've heard entropy used several times today, which is good. And flow and magnetic refrigerants are important concepts. So you not only had to understand so one of the people here today said they don't teach magnetic thermodynamics to any of you any longer. Well, if you do that, if you take and say, what is the total entropy change for a case where the 2 principal variables are are temperature and magnetic field. What you will find is that you need to know the adiabatic temperature change, which is on this plot, delta T versus T, and you need to know the field-dependent heat capacity. So here is the heat capacity usually used for looking at is the standard Debye equation plus a little bit of electronics if it's metallic equation is a function of temperature. If you put a magnetic phase in there, in this case it happens to be gadolinium nickel, you end up at the Curie temperature getting this very large change in the heat capacity. And at different fields it changes in the following measured way. And so this happens to be data that we had to measure. When I was at Los Alamos, we didn't have any of this data really at all. So we measured all kinds of compounds, and this is still going on. There are now, I think, something like 300 publications in magnetic refrigeration and magnetic materials, and there are probably 100 patents in this area from all different places around the world of things. These are both very important. You need to have both these pieces of information to do a complete simulation of the magnetic system. So, okay, now, that's one of the things that got me started. I was at Los Alamos, and I do take this lesson seriously. I think you should all be business people, but I know that's probably not the right thing for all of you to do. I think you should also all be great scientists, and that is not the right thing for all of you to do. And so you have to make those choices yourself. I know that when I came here from Notre Dame, I was pretty high up in the class at Notre Dame, and this is a great humbling place, okay? I think that there were 30 or 40 of us in the thermodynamics class, and I realized I wasn't at the bottom of the class, but I was a long way from the top of the class, okay? And one day somebody wore his, I think it was his, Phi Beta Kappa key in, and the next day, 2/3 of the class came in with their Phi Beta Kappa keys on, and put that person into appropriate position. But anyway, long and short of it, this is a fantastic place. You guys are all very bright, and I respect that immensely. I think it's really important. And so some of you want to be entrepreneurs, and I respect that. I think I would encourage that. But it's not for everybody, and I'm going to tell you a little bit about why. Anyway, Stevenson-Weiler Act in 1981, and it was passed. This is a technology transfer act. This was driven by the Congress saying, my golly, we're spending Los Alamos budget that at that time was $300 million a year or some big number like that. And they had all these neat projects that we did, like the spittle and all kinds of other projects. We would work on them for a year or so and get the results, publish the paper, and take it down to the basement, put it on the shelf. And I know that doesn't happen at universities like here, but it happened at Los Alamos. So what happened was they passed this act that says every national lab had to spend a portion, a small portion, of their budget on transfer technology out of the lab, commercial. And certain Los Alamos National Lab projects with potential commercial application were selected, and magnetic refrigeration was one of those projects. So they said, hey John, you're a PI on this project, why don't you think about considering transferring this technology out of the lab? And so I don't know much about that. And so one of the people, the professor from the University of New Mexico, said, why don't you take my course, my graduate course, in technical entrepreneurship. What a wonderful topic, okay? And indeed, this was a great course. It taught me how to write a business plan, so to speak, and so I thought. Anyway, I wrote my first business plan as a course project, and at the end of that, I realized that I was trying to create a new company. I created the first company, Thermomagnetic Devices, and the business plan was probably 100 pages thick, and a few people started to look for money, and I was trying to raise $5 million. And again, amazing amount of money, but that's what I tried to do. And a company called Astronautics Corporation of America had just set up an advanced technology center in Madison, Wisconsin. They were based in Milwaukee, and they were about $150 million a year company, aerospace company. Most of the planes that were flying back and forth across the country had at least one of their instruments in the cockpit. So all of the different attitude indicators and horizontal stretch and all of those kinds of instruments like that were built by astronauts. So it's a good design manufacturing company. They said, we love your idea. We'd love to have magnetic refrigeration because they were interested in space. They wanted to build cryocoolers for space. That was part of their business. extended business, and they needed a group to do that. So they said, okay, we'll invest $5 million, but we won't do it in New Mexico, where this company was created. So this is a company that got created and then went into oblivion. You know, never ever hired anybody. Just created, incorporated, and then went out of existence. So, but Astronautics said, you guys come from Los Alamos to Astronautics in Madison, and the lab had set up this wonderful program. For 2 years, you could leave, and they would welcome you back if you failed. And so, wow, that's a wonderful safety net. And so four of us decided to do that. I led that group, and the two of them actually did go back out of the four. The other one is still at Astronautics at the moment. And anyway, they did invest more than $5 million, actually about $8 million in this. And I became eventually the manager when I started, and eventually became the director of their technology center. And we did all kinds of neat things there. But mostly we worked on advanced magnetic refrigerators. And one of our awards was from the Strategic Defense Initiative. We got the Best Cryo Cooler of the Year award. And that was pretty neat. This was, of course, thinking about, okay, how do you put interceptors and all kinds of other things for rockets and neat stuff. But there was another program that we worked on, which was the National Aerospace Fund. And I have a patent on making slush hydrogen, okay? Because slush hydrogen is liquid and solid, 13.8 Kelvin, 50-50 mixture. It has a higher energy density than liquid hydrogen, and there are 2 or 3 ways to make it, and we created a new one, and actually got a patent on it. And I got that patent was allowed before I left Astronautics, at about 1992, it was allowed, and it never got issued until about 2 years ago. And it was because it was national security. So the national security said, no, you can't issue that patent. It's allowed, it's accepted as a new invention, but you can't issue it. And so I just all of a sudden, a couple of years ago, get this announcement, yeah, your patent has been issued. And I said, what? And so I just found that out. Anyway, fun stuff. But what I was learning was a lot of good business skills. The CEO of the company was the founder of the company. He was a very, very good cash flow manager, and he would take me down every week down in Milwaukee, go through essentially 4 hours of tutorials on how you run a business. Great learning. The thing was that they were government business, and so what I did is I went to the board and I said, hey, look, I'd like to form a commercial division for the company, and they said, no, thank you. We're going to stick to what we know, which is government business. They're very good at that. And so they turned me down, and so I decided to go form my own company. So I resigned to form a design manufacturing energy company in Seattle, and I formed Cryofuel Systems, Inc. in 1993. And I realized, though, from that tutorial was that I needed something that created revenue. And I'll show you in a minute why I focus on liquid natural gas rather than liquid hydrogen. I couldn't see anybody that would buy liquid hydrogen systems, okay, enough to sustain a company. And so I chose to focus on liquid natural gas, and I'll show you why in a minute. But at the same time as I was going out there, I was approached by the University of Victoria, British Columbia, and they offered me an endowed full professorship in mechanical engineering. So I'm probably one of those unique people in chemistry that's been tenured in physics and mechanical engineering, but never in chemistry. Okay? So that's, it just means that you learn how to learn and you keep doing it. Anyway, this is a really interesting group. I had about 12 graduate students at the maximum. We did a whole bunch of R&D related to liquid natural gas. We looked at every one of the liquefier technologies. We looked at a whole bunch of purification technologies. Really start to learn how to do chemical engineering in a big way. But this Institute for Integrated Energy Systems there really created a lot of new ideas. And I taught graduate and undergraduate course in cryogenic engineering, properties engineering materials. As a fun, I really enjoyed teaching, and that was a lot of fun. The difficulty with this was that it was an opportunity to avoid being a dinosaur. When I was the director of the Technology Center in Madison, I had a full-time personal secretary, I had a clerical secretary, and I had a clerk that filed documents and stuff like that. So I had 3 people supporting me, and needless to say, I was incapable of running the new DOS computers that came in, and had to figure out how to do that. Went to university, of course, you could do all your stuff yourself. And so that was interesting. It got me away from being a dinosaur, and that's really important. Here's one of the things, the lesson I leave with you, really important. These are the Marchetti curves, they're called. They were done by the Integrated Industry Systems Institute in Vienna. And I'm just going to flip through these so I can talk to them here. This is the Marchetti group at the International Institute for Applied Energy Systems Analysis. And he plotted here, this is a percent of total energy use from 1850 up to 2150 as a function of the different mixes of sources and uses. So the solid lines are their projections for the different fuel forms. This was the solids, the liquids, and the gases. And the thing they did differently from way back from the Club of Rome and a bunch of other really interesting early first energy crisis kind of calculations is they just froze technology now and projected what happens 20, 30 years from now. Bad idea, okay? You tend to get very erroneous results. You have to let technology evolve, and that was really important. They did that, and they came up with these curves. So the thing that struck me is 2 things. One, the lines like this are the actual use data, and you see that those are actually not far off of what's happening. And now, of course, with shale gas, the methane thing has jumped way up to here, out here in 2012, and oil is continuing to go down, and so is solids. But what you see is sustainable economic growth. This is where all of a sudden, bingo, light bulb went on. That's something that made sense to me. That sustainable means it's repeatable and for a long period of time. Renewable means you can repeat it. It's even better. Okay? But decentralized, less capital-intensive technologies, and that was really good. And you can see methane and hydrogen. So these are gaseous fuels, no longer salts. So that says liquefaction is really important. You better be able to make good, efficient liquefiers. So that reinforced what I was already working on before, and it was good. Now, the other second thing on this is that these curves are not depletion-driven. They're technology substitution-driven. And that is so key to understand. We're not running out of coal. We have lots of coal. If we use coal and just burn it the way we have, we are going to choke. Okay? Too much CO2. Okay? So there's a bunch of implications of that. So we have better technology, and a perfect example, as much as it is debatable that it's all good, horizontal drilling and fracking. That has changed the whole way the United States is looking at energy systems. The amount of natural gas we have available is just huge. It has big impact for energy security and much less expensive fuel and so on. So that's the key thing that I want to just leave with you. The second thing I want to show you why I went into natural gas is here. I looked at U.S. energy. How many people know in the room, you write down on a piece of paper how much energy we use per year in the U.S.? Everybody? I hope so. Okay? The answer is about 100 quads. What the hell is a quad? Okay, great unit. Okay, definitely not SI. It's quadrillion BTU. Okay, 10 to the 15th BTU. That's a quad. And that's a unit that the Department of Energy and the Energy Information and a lot of the industry in the United States use instead of the proper SI unit. Anyway, about 100 quads of energy are used per year, and here's where we get it from. Coal, natural gas, and renewables, nuclear, and petroleum, where it comes from. And this is a little bit dated. I have the 2010 data. I just didn't get time to put it in here. Not so different. And then I looked at the petroleum, and you see, my God, look at 63% of our transportation will come from petroleum, which we know. And unfortunately, of this petroleum now, we're about 50% imported. It was higher, but it's getting better as we start to have more and more indigenous petroleum in the United States. But we were importing about 60% of the petroleum a few years ago, and it had an enormous impact on the balance of payment. The deficit was huge, and that largely comes from almost $1 billion a day, I calculated, that we pay every day, that we send offshore. Okay? That's taking money out of all of our pockets, sending it over. So, this was a big one to me. Said, wow, that's important to look at. And then I looked over here, this little 1/10% that you can barely see the little line there, I should have picked a better color, is the transportation sector supplied by natural gas at 2005. Unbelievable. I said, why? We should be taking a big chunk of this and using natural gas to do that. And that's what the light bulb went on. I said, my God, that's a great business opportunity to look at. Be part of that transition. And that's what I proceeded to do. That's why with cryofuel systems, I went ahead and focused on liquid natural gas because I thought it was important. And when you did the market studies on this, which we did quite a good ones out, it clearly, evidence was that lack of refueling infrastructure was the key barrier. Why? Natural gas is a great fuel, cleaner, safer, cheaper, and why wasn't everybody using it? Well, the reason was it wasn't available. So, just to show you some of the plants that we did, this is the stranded well gas, the liquid natural gas plant that was operated in Central California. The gas well is out in the middle of that great field back over there, and that comes down under a pipe under this road, about a mile, comes into the plant, and comes up over here, and then goes through TSA, temperature swing absorber bed. These two beds purify the CO2 and water. Here's the screw compressor back there. That was a single screw compressor. Here's the genset for the power. The cold box is back here, and here's the LNG storage tank, about 15,000 gallons LNG storage tank. So this made about 5,000 gallons every day, and it ran very well. All of this is great applied chemical engineering. So you know, block process flow diagram, PFD, PNIDs, all of the different stuff that you do in chemical engineering. You learned all that basic stuff is applied here, big time. Plus, this is all designed to code, very in compliance with about 20 different codes that you have to build to because you're doing energy. So, anyway, this produced about 300,000 gallons of LNG, and then the well decided to go south and didn't have enough gas to make the liquid. Here's the other end of that plant, just to show you that here's that storage tank. Looking at it from the other angle, there's a bunch of controls. This whole thing was automatically controlled. I actually ran this plant from my hotel room 40 miles away from this and could do that on my laptop. If I had the program, I could load it up right now and run it from here. And pretty soon, when Renewable Energy Northwest gives, this is going to be on here, okay? And I can give you this plant, I'll be able to control and run a plant like this from my iPhone, okay? And, or iPad. And anyway, this is, you hook up, the truck comes in here, there's a scale, you can drive onto the scale, and then you connect up the LNG line, and then the vapor return line to the other line, you ground everything and do all the things according to safety, and you then turn the pump on, the driver's over here, he programs in, I want this tank to weigh just under 80,000 pounds with vehicle weight when it's full, all automatically done. And when it gets up to close to 80,000 pounds, the pump automatically shuts off, comes over, and does a reverse process, loads up, drives away, takes it to a customer. And that's the way you take about 9,500 gallons of LNG away at a time. Okay, now today is Halloween, so this is why I put this first sentence in here. Expect surprises. If you become an entrepreneur, I guarantee you are going to be surprised in almost every day. And it just goes on. So you have to anticipate that, and we didn't anticipate all kinds of things. I had a $6 million investment by a wealthy Mexican company. We had been through 3 months of due diligence, of looking at everything. They liked what they saw. They gave us a deal. We said, great. And we were 5 days from signing the paper, and the peso devaluation occurred. The peso dropped by 40% in value, and they shut the deal down. So, boom. And boy, it hits you right about there. Fifth round of financing, $5 million was 2001, .com. Boom. Now, was I smart enough to figure that out? I guess I should have been. When people are saying it's got a new economy associated with the .com bust, blah, 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 or .com business. But the reality is that I had one angel investor lost $14 million in 2 weeks' time. And needless to say, he wasn't interested in investing in my company. So that is the kind of thing that happens to you. Champions. East Ohio Gas big gas company. We had a great project with them, going really gangbusters. They had built a prototype and everything with us. And then they decided to re-engineer companies, big companies, and they decided to change people around and find out where they best apply and all that stuff. Both of my internal champions in that company got reassigned, and the program died. So, bipolar personality, this is a pet peeve. I don't know how many people have run into bipolar personalities, but I guarantee you I have now a chapter in my book I'm writing is there are at least 3 that I will describe in detail in this book, but one of them actually wrote out a $1.8 million check, which I still have, okay, for a deposit on one of our plants. $1.8 million check, I have it. All right? It's actually now in a little package, okay, to preserve it. But he said you can't cash it until I give you the okay. I still haven't been able to cash this check. And this guy is really a bipolar personality. And then the other thing is you have very little time to recover from mistakes. So in small companies, you make a mistake, and bingo, you're likely to be out of business. And the problem with that is that, and I put Avis down here, there's a great book by the founder of Avis, Renewable. He said if you make 2/3 of the decisions correct, you're doing very well, and learn from the other third, and you're going to be very successful. So if you do that in a small company and make 1/3 wrong, you're likely to be out of business. And that's why I thought 1 in 10 or 2 in 10 of small companies survive. Okay. Anyway, I didn't go belly up. I didn't go bankrupt like I should have potentially done. I licensed the technology to Prometheus Energy Company. And they then had all this technology. They realized that, my God, what do I do with all these drawings, the documents, and files? We had to have somebody that knows know what to do with it. So they hired me as their CTO, and they took most of my group with me, and we developed a lot of advanced technology for Prometheus Energy Company. Here's another example. This one here is the one down at Bowerman Landfill in Irvine, California. This is a landfill gas to LNG system producing LNG from some of the dirtiest gas you can possibly imagine. And so really a lot of good engineering that went into that. Here's the Jenbacher, the 1 megawatt power plant that ran off of the gas that we cleaned up from back here and put into that plant. Here's the scale. You drive a truck. This scale is sensitive enough that I could tell which driver we had. It's probably the nearest pound, and I could tell it. And you could tell whether they had a big cheeseburger for lunch or not, even though. But this is that tank, the back end of the tank where this LNG is sent off to. And here is the loading system that you load the tanker. The tanker looks like this. This happens to be actually an LNG truck. That's about 9,500 gallons of LNG that Prometheus Energy Company is taking to market. One of the customers was Orange County Transit Authority that ran LNG in some of their buses. But the better one was the Class 8 garbage truck, the transfer truck that collected all the garbage from a certain city and the nearby area. They filled up with LNG that came from the landfill. So talk about a wonderful story. You see them come into the landfill, and you see that they had a blue truck head on their body. And you can say, my God, that's one of our trucks that we're fueling the landfill gas that came, the LNG in that truck that came from landfill. And that was really satisfying. So you get some nice things that happen like that as well. But that's a renewable. That's waste to LNG. That's a really nice thing to think about. And there's a lot of people that today are talking about anaerobic digestion of waste streams of various kinds that convert that to biogas. And we know with this technology how to clean it up and put it into a very valuable fuel. Okay, Renewable Energy Northwest is my third company. And the reason that's a third company is because the Prometheus Energy Company, about a year ago, decided that their board decided they were closing the Advanced Development Division completely, and they eliminated Chief Technology Officer role. So I had an employment agreement. I got paid out for a certain period of time, and then I'm out of a job. So, but they did say, why don't you form another company? So I did. I said, sure, this has been there before. I'll do this, and I did. And so about a little over 15 months ago, I formed Renewable Energy Northwest. It's an LLC. There's some good reasons for that. It's a limited liability corporation versus a C corporation, which is a standard Inc. But this is my third. And I'm applying lessons to learn from these first 2 experiences. And so I have about 12 things. One of them is get cash flow positive very soon. Another one is raise more money than you ever think you're going to need. Okay. Another one is hire the right people, and goes on. Because all these mistakes that I made, I'm trying to learn from, and if they don't change me, then what useful exercise was it? So this enables participation in the great wealth transfer. There's a big wealth transfer when you change from oil and gas to natural gas in this country. You take a lot of money out of this pocket, you're going to put it in this coffee, and you might as well participate. If you ask Shell, how do I participate with you on a project? They'll say, buy stock and roll that Shell. That's not very satisfying because it's such a humongous company that incremental change to natural gas is small. But if you buy stock in Emerald Energy Northwest membership, you have an opportunity to grow immensely. Optimistic, okay. Vertically integrated energy and service company. It's an LNG supply, and the same thing as I mentioned early on. When we talk, and I'll show you in a minute, you still need supply. You would all be driving a natural gas vehicle or natural gas powered assisted bicycles, probably. No, if you had refueling stations where you can save over that $4.25, the same gasoline gallon equivalent price for natural gas, $1.99. Same thing. And you can buy some great vehicles running on natural gas, you just can't get them refueled. And so it kills you. And the key thing is that it's a great value proposition for customers because of that. Let me just quickly go through a couple things here and I'll be done. This is make realistic targets for LNG and CNG refueling infrastructure. So I wanted to be sure I was not smoking something that I shouldn't be smoking when I did these numbers. So 10% penetration by 2020. So 10 years from now, what does that mean? We use about 100 quads per year, 25% total for transportation. Total energy, we use about 25% for transportation. Most of it still comes from diesel, but we could get a lot of it from natural gas. If we use that from natural gas, it's about 1,000 BTUs per standard cubic foot. That's about this many standard cubic feet per year. Go through 82.6 standard cubic feet per gallon of LNG, gives you about 300 billion gallons of LNG per year, 830 million gallons of LNG per day. That's how much you would need to all of the transportation sector. So we're going to take 10% of that. So we need 83 million gallons of LNG today, every day, to be able to supply 10% of our day. These are big numbers, okay? But this sounds awful big compared to what we have available at present. But when you then say, okay, what we're planning to build are 50,000 gallons a day plants. And if I do that over 10 years, 1,660, that's okay. That's manageable. I can see that happening. So this is a reasonable number. And for all the rest of the stuff, the investment is about $6.5 billion per year. Again, that sounds like a huge number, but it's very manageable from big company finance kind of thing. So this is also doable. Gross revenues, 16,000 stations. There's about 160,000 stations in the United States. Okay, that those 10% of 16,000 where you could refuel. Just run all the numbers. It's about $37 billion a year. So this is actually not bad. $1 million a day is the business cash flow that you're talking about. Really serious stuff. We're going to participate in this in a big way. And our plan is to get to 10 plants, 500,000 in 5 years, 500,000 gallons a day, and that's a very nice, attractive thing. Just to quickly finish then, Class 8 trucks, $70,000 a year. This is the fleet customer problem. Engine emissions are increasing costs dramatically. They have to comply with EPA reduction of particulate matter and NOx. Very powerful constraints. The escalating costs are squeezing profitability. Some of the big companies that run these Class 8 trucks are just barely above the waterline. They're really struggling. It's just costing them so much for this, by the way, is about 100,000 miles a year for a Class 8 truck. That's not the maximum by a long ways, but it's a reasonable number. And the key thing is because of BRIC, I mentioned that before, diesel cannot solve the problem. It's not going to come back down to $30 or $40 a barrel. No. So you're never going to see diesel fuel prices again, in my opinion, at $2 a gallon, equal to what we can sell. So that's one of the key things. The next thing is that if we go to the solution, if this customer, same truck, running on natural gas, makes equivalent $43,000. They save $27,000 per year, per truck. And it cost them about $35,000 extra for that OEM certified warranty truck. So it means that they, in a little 15 months, they've got all their initial investment paid back, and after that, they save $27,000 per year. That's huge to a trucking company. And it also, natural gas already meets the EPA emission easily. And the key barrier is lack of LNG supply, refueling infrastructure. That's where Emerald Energy Northwest comes in. We enable this solution. So here's a design package that we would do. Here's a plant. I showed you already this. Here's a refueling station where you would actually do. We offer this complete package. We do all of that in our company. Here shows you the fuel. An average of 23,000 gallons, almost, well, class 7 and 8 is over 50% of the fuel used in the United States is in this class 7 and 8 trucks. So it's a very important, big market. That's why Boone Pickens is saying we want to sell to heavy-duty trucks. It's because of this very curve, okay? And you've seen that on, and we want to do that too. It makes a hell of a lot of sense, and it's cost-effective, and so on. Lesson 13, learn how to do financial projections. If you're at all interested in business, you better learn how to do financial projections really well. Understand them. Even if you hire a good CFO, financial officer, to do all your numbers, you need to understand them. They're really important. So here it shows the gallons production per year, per quarter. This is almost $60 million per quarter out at the end. Here is the Emerald Energy's, it's about $45 million of annual revenues, and its income is about $20 million a year. So all those things are pretty solid, and they're attracting investors as we speak. So, lesson 14, keep pursuing promising sustainable renewable. And you guys all should be doing it. Every one of you should be thinking about, okay, how can I make a contribution to something that's like this? And I give you 4 ideas. The number one is already happening. This is a shale gas, pipeline natural gas to liquid natural gas, plug and play. So this is saying, oh, look at that big plant that you saw spread out all over the place. That's the standard skid-mounted chemical engineering plant. Let's package that in nicer containers and then just do like Dell does when I get my Dell computer. I take out the computer, I take out all the color-coded, and I do all the connections, and within 40 minutes or so, I've got a computer functioning. I want to do the same thing. I want to paint every pipe different colors, and I want to have the plug-and-play capability to hook up a plant and do that. And I'll show you a picture of that. Methane hydrates. There's about 2,000 years of natural gas at the present usage rate that we have in methane hydrates. Huge amount. So this is reasonably sustainable. Not renewable, but it's sustainable. Innovation is required to capture this from high pressures, low temperatures, and or deep sea systems. A methane hydrate is just a class rate. Basically, it's got 4 or 5 water molecules around a methane molecule. That's what a hydrate is. And it actually is a problem in pipelines. If you have water in a high pressure pipeline, then you'll end up getting plugging in the pipeline due to this hydrate. So it's a problem for the oil or gas industry, but it also has enormous amount of methane recovery. This is confirmed by DOE and so on. Gasification of coal. This is a really interesting one. If you put hydrogen into coal gasification, you don't get CO2. So normal coal gasification is water, and then you get carbon plus oxygen to get carbon dioxide. That's what this doesn't do. So this is the simplified version of that, but it's been done at a high temperature fluidized bed combustion. And Arizona Public Service actually built the system. I've seen it. It's probably 3 times the height of this building here, of this room, and it was something that you can almost walk around easy with your arms. And it about 1,600 degrees, direct hydrogen injection in coal, bingo. It's beautiful. Now you have methane. You can deal with methane, and we know how to do that, and it's really quite interesting, and it doesn't produce CO2. So that's something of interest to me. LD to biogas, the liquid biomethane. This is the one I've talked to several of you about, but there are about 250,000 species of algae. It grows about 30 times faster than terrestrial-based biomass. So it's renewable because it uses solar photosynthesis, and it has a lot of promise. You can take that algae biomass, put it into a digester, make biogas out of it, and now you saw the technology for making liquid biomethane, liquid natural gas from it. And I've done all this numbers on this system. They do look quite promising. And if you take about half of the land mass in Alabama, not too many people from Alabama here, but if there are, take about half of your land mass in Alabama, grow algae instead of fish in your fish farms there, and catfish farms, and what you will have is enough energy to supply 20% of the nation's transportation needs. So that's it's not like, my God, I need the whole landmass of the United States covered with algae farms, or the whole half of the ocean. It's very reasonable, in my opinion. Okay, here's my plug and play concept for what a plant looks like, and all these will just be dropped in place. They'll be interconnected, and that'll be a very fast, flexible model. All these things that you get, which are seen as important. Here is a block process flow diagram. I thought I should have one of these in for chemical engineers. So biogas comes in, pre-purifier, bulk purifier, liquefier. You make LNG out of that. You've got power or refrigerator, instrumentation control is really important. Here's your algae growth. Here's your digester, and this gas would come down here. And I've just left it at that. But we've done a lot of analysis on this kind of thing. And the thing that's interesting about it is that this needs CO2, so it's a method of sequestration for CO2. It also gets CO2 from the bulk purifier where the CO2 is removed. About 20% comes from here, 80% from other sources. And you can feed these algae and they will grow very fast. There's a very clever ways of capturing that algae, and you don't have to, you're not trying to make lipid-rich algae, okay? They grow proteins and carbohydrates and lipids, and so you don't care. You let them grow, and you kill them and put them into a digester. They make biogas very nicely, and there's a lot of synergy. So, okay, there you go. Last lecture. Okay. First of all, this is really important to appreciate. I hope that energy technologies, vehicles, and for all energies, really cross-link so many different things. It's really important to understand these linkages, in my opinion. And so I encourage you to be students of these studies. I believe that methane is a great hydrogen carrier. CH bond is very powerful in a methane molecule, and it's a great way to carry hydrogen around. So carbon becomes a great carrier of hydrogen. And if you did need hydrogen, because you can easily reform methane to make hydrogen, you have a bridge to hydrogen supply. So those are two of the things I think are really important. Obviously, liquefaction is key in that too. If oil stays at $100 a barrel, I made that point. The supply and use infrastructure is a major challenge, but it's a great business opportunity. So then finally, I urge you to find your passion and pursue it with enthusiasm. Most of you that I've talked to, clearly you're already doing that, which is wonderful. Be objective and open-minded, but let the numbers decide. Really important. Do the numbers. If you're not massive users of MathCAD, then time out, okay? But use MathCAD. So you run MathCAD and everything should be numbers, okay? When you're making decisions about some new ideas. Remain optimistic without losing touch with reality. How do you do that? I don't know, but that's a good thing to try, okay? Be flexible and innovative, goes without saying. Be lucky. This is really important, okay? And then the last one that I love this one. Choose your parents wisely, okay? Because to make a big impact, you have to live a long time, and this is really important. Okay? And you have a lot of control over that too. But and then finally, enjoy it. Okay? Thank you very much.
Okay, so we have time for one or two questions.
What about magnetic refrigeration for air? Is that reasonable out there?
It is. Yes. There's actually, Praxair actually filed a patent on exactly that application, John. Okay.
It's not yet,
It's not yet industrial, but they thought it was worth spending $8,000 or so to file a patent on it. I think their patent's a pretty good patent, so I think it's sweet. I would say we're about 3 years away, in my opinion, from having a magnetic liquefier. I didn't show you some of the advanced development prototypes that was built. We built prototype up at Prometheus Energy, and just one stage span, over 50 Kelvin. Gadolinium alone, over 50 Kelvin, and now the layering other materials into it, and that's what happened when the Prometheus board decided to shut down the advanced development, as that program went into limbo. So it's still there, waiting to be done once we get back in line. But about 3 years, I'm hoping that there'll be a small commercial prototype of magnetic liquid. Yes?
You talked about using 1,600 different stations or different plants to make it liquid natural gas. Are there not like sources to have a distributed amount of those types of plants in the U.S.?
Actually, they've used up just about all the LNG that's being made today in the United States.
Not taking up the feed into that, the gas version, the natural gas well.
Oh, there are lots of gas wells, but they don't make, obviously, liquid. So there's a large number of shale deposits in the United States that have been discovered, and they're injecting that gas that they recover out of those wells from into the pipeline structure. And there's a complete national grid of pipelines all over North America. So we use a hub and spoke model. The largest distance we hope to carry liquid natural gas is 150 miles. So we have a plant, and then around it, the customers exist within 150 miles. And so that plant will be located right near a pipeline. So it's a very short connection to a pipeline. But there are about 100,000 stranded wells. Just wells have been drilled out in the middle of nowhere. They've hit gas. They don't have any way to monetize that gas, so they're shut off. So you could go and talk to those people and buy that gas from them as one potential source of gas. Does that answer your question? Yeah. Okay.
So you talked about more sustainable technologies being decentralized and less sustainable being more centralized. But when you look at a lot of the bulk chemical production, you see that even working on a larger scale, there's huge economic savings to that. If you look at companies like Dow centralizing ethylene production, that sort of thing. How does that balance play in here?
That's a good question. I think it depends on what you're doing. Okay. First of all, there's a common scaling equation in chemical industry and lots of other things is the capacity to the 0.7 power is related to the capital cost of the plant. Okay, so that's one of the things you have to look at. As you go bigger, then it gets more cost effective per unit product out. And the same thing is true for these systems, other than the fact that the offset of that making it bigger is the replication of identical systems. So you have the economies of replication versus, and making these in a factory, which is a lot less expensive than doing a field erection of a big plant where you have to pay a lot of people to crawl all over the big plants to make them work. So I would say it's because it's an energy related versus a chemical industry related. And there are big companies, if you talk to Royal Dutch Shell or BP or any of the big oil and gas companies, they will say we are going to build bigger versus smaller. The complication there is that the cost of distributing the liquid natural gas and those tankers that I showed you there is quite expensive. So if you wanted to bring from Southern California to Seattle, it costs you 45 cents a gallon to get the gallon of fuel up there. Whereas us, making it in near where we use it, the maximum that we pay is 7 cents a gallon. So so the economy of scale that they get from having a large plant tends to be eroded by the fact that there's a transport cost in the liquid natural gas case. Okay, so I think, and the other thing is, I particularly get nervous given that we live in a new world. Okay, since 9/11, that there is going to be a scrutiny on how do we do damage to different parts of a system. If you have big lumped sources of energy production, I think you're setting yourself up for a serious impact. So if it knocks it out, boom. I mean, just look at New York City, okay, and they lost power, and wow, the impact. So if you had a big power plant where it was centralized, or a big LNG plant where it was centralized, and they targeted that, it would have a major impact on the fuel. So chemicals industry, I think if that's a concern for them, they should probably distribute it. But if it isn't, then I don't see any reason to do anything but go bigger and better. So, is that, yeah, okay, great, yeah.
Okay, let's save the rest of our questions for the reception, and thank Dr. Barclay.
Thank you very much. Different forms of energy was one of the topics. So we talked about chemical, potential, nuclear, gravitational, and we did the calculations, for example, of how much nuclear waste would be involved for producing all the global energy using nuclear. And got some staggering numbers, and so that sort of opened some of their eyes. We did chemical potential and looked at that, a lot of good examples, gravitation, so on. And the students sort of got this idea. The thing that got me was interesting that we can do energy conversion. First of all, they always thought energy is used. So teaching concept of conservation of energy was something new. And that was interesting. We did that. And you convert from one form to another, and most of these are semi-reversible. But most of them also have some aspect of that conversion that turns out to be thermal energy. And so you go to all these different lists, and you can go to just about anything you can think of, converting one form of energy to another form of energy, and you end up with thermal. And once you get to thermal energy, the key point that I learned way back then is you can't get it all back. Okay, so you're locked into this heat trap, and that to me said to me, my golly, I better really start to study thermodynamics. And I begin to do that and seriously trying to understand how you manipulate thermal energy to the maximum possible efficiency. And so the heat trap is a very important thing to understand, in my opinion, and the applied thermodynamics is, of course, incredibly important to chemical engineering, and so it's important to do that. Third lesson, choose relevant topic projects. And this, after 8 years in Australia, I was on a speaking tour, went around the world. Australia is a long ways away, and I wanted to continue to interact with my colleagues, and I was on a speaking tour, and ended up giving a talk at Los Alamos National Lab. And it wasn't too long after that that they said, my God, we've got a perfect job for you. Would you like to apply for this? And I said, wow. And I said, yes. It was in the energy division, so it's outside the fence, as they say, so I wasn't working on weapons. I was working in energy system, and they wanted to work on this particular condensed matter and thermal physics group. They were working on cryogenic engineering, low temperature physics, and that just fit perfectly with what I've been working on at Los Alamos. By the way, my PhD was done up at the Rad Lab with David Shirley, and we were doing work at about between 5 and 10 millikelvin, looking at a whole bunch of interesting, neat things that happen when you cool samples down to those low temperatures. So, and he had done his PhD with Professor Joke. And when I came to these seminars over in the chemistry department, occasionally Professor Joke would come in and sit down about right there where that blue sweater is, white hair, retired already, and he would, at the end of the seminar, ask 3 or 4 incredibly penetrating questions. So you can try that on me. You may not get the same kind of answers as he expected to get.
I'll leave that to Dr. Prescott.
Okay, there you go. So basically, Los Alamos is research heaven. It's a place you go when you want to learn an immense number of new things. And I learned all kinds of thermal physics. I learned how to do very elegant computational fluid dynamics. I learned how to do materials work, all kinds of things. And anything you don't know, about 3 phone calls, and you find somebody that knows the answer. And that's why I call it research heaven. And you had a lot of money, so that was very nice. And I was recruited for applied superconductivity projects, and so I began to explore efficient magnetic refrigeration. And this was something where obviously I knew about magnetic refrigeration because I had gone down to 5 or 10 millikelvin using magnetic refrigeration, but it was from 1 Kelvin down to 5 millikelvin, not upwards. And that's the classic magnetic demagnetization, adiabatic magnetization that you do. Well, a colleague, Jerry Brown at NASA Lewis in Cleveland, had done something really quite remarkable. He had taken gadolinium metal, it's a ferromagnet, at room temperature. It has a Curie temperature just about 300 Kelvin. And he had turned it into thin sheets, put it into a magnetic field, and its temperature increased to 7 Tesla magnetic field. Temperature went up by about 15 degrees. And then he put it through, he moved actually a column of alcohol and cooled the magnetic material down by this column of alcohol, which had a temperature gradient in it, and then demagnetized it. It cooled the bottom of the column of alcohol, and he moved this column of alcohol back and forth when he magnetized it, demagnetized the thing. And amazingly enough, with the 15, energy is also strongly coupled to the environment. It's critical that if we just go ahead and do business as usual, for example, to say we're going to provide all the energy that these countries that are changing, going from third world to first world countries, we will choke on CO2 because it's going to be coming from high carbon fuels. So climate, and Sandy is a good example, one of the largest storms that occurred today. Well, greenhouse gases, air quality, California is way up the curve on these two. I'll show you a project later on that we did in the South Coast Air Quality Management District in Southern California, and it's one of the toughest places in the world to get a permit to do something related to the environment. So these are all related, and they're really, really important. Finally, what I want to leave you with is it's important to understand and improve energy systems. If you don't take anything else away from that, make sure you understand that because it's going to be a really critical thing. Lesson 2, understand the heat rate. I'm going back to beginning, okay? After I left here, I took an Australian Institute of Nuclear Science and Engineering postdoc at Monash University in Melbourne, Georgia. About 15,000 students. It was a relatively modern university, but very good. One of the top, say, 10 or so universities in Australia. And eventually, I finished that 2-year postdoc and got offered a position as a chemistry graduate in the physics department. So that was always a little bit interesting. And one of the things that 3 of us did in the young lecturers was to develop a new course called Physical Science for Non-Scientists. So we were trying to say, how do we reach out to the other people at the University at Monash and introduce them to energy systems? And that's actually quite an interesting question to answer and address. And what we tried to figure out, what topics would we teach? How do you teach somebody that's had maybe general science at freshman year in high school and no science beyond that? How do you teach them what the concept of temperature is? How do you teach them what energy is? How do you teach them what all kinds of other things are when you're trying to describe energy systems? And of course, one of the things that we were looking at is how
I am pleased to introduce our speaker for today, Dr. John Barclay. He received his PhD right here at Berkeley in physical chemistry, and he went on to do a wide variety of things in alternative energy. So currently, he is a managing member and a CTO of Emerald Energy Northwest, and he has 125 publications and 15 patents to his name, and he's won numerous awards. He was also previously the CTO of Prometheus Energy Group, which is currently up for a major award. And he was the founder of Cryofuel Systems, all in the Seattle area. He previously was a professor at the University of Victoria, British Columbia, and he led the Advanced Technology Group at Astronautics Corporation of America. And Dr. Barclay may not realize it, but he actually was a household name at my house growing up for a number of years. My father worked for him back when my father was about my age at Astronautics. And so when we were coming up with speakers to invite, I immediately thought of Dr. Barclay for that reason. And also when I chose Berkeley, my father immediately told me, oh, well, Dr. Barclay, he went there. Okay. With that, I am pleased to introduce Dr. Barclay, and please join me in welcoming him.
Thank you, Amber. Her father was one of my most creative design engineers. So, I'm going to try an experiment here. This is an opportunity to sort of transmit some experiences that I've had over a very enjoyable career. And it's a wonderful statistical thing, problem that you do, the drunken sailor walk, okay, that problem. And my career seems to be a little bit like that. It seems to go lots of different places. But those all were related to something that I was interested in doing, which was related to advanced energy systems and research associated with that. So I'm going to go through this talk. I'm happy to answer questions depending on how you do it, but I think it's probably better to walk through this and then ask questions at the end. But that's totally, however your format is, I'm totally comfortable with either one of those. Okay. So let's start, and I will first of all say thank you so much. It's a great honor to be back. I did actually leave here in 1969 with a PhD in hand, and 2 weeks later I was in Australia, and I was on a fellowship there, and that's the beginning of a path. But to come here in 1964 when Mario Savio was down on Sproul Hall steps speaking about free speech, and having come from University of Notre Dame, which is probably one of the more conservative universities in the country, to Berkeley, which is one of the more liberal universities in the country, it was a very interesting experience. And part of the reason that I believe I am a reasonably objective, open-minded scientist is because it's forced upon you, okay, when you come to the University of California, Berkeley. And so, anyway, let me start. I've got a series of lessons that I'd like to share with you. The first one is that there are about 5 billion people in the globe that would like to live like about 500 million of us do. And that is a huge thing that's happening. And you may have heard the acronym BRIC: Brazil, Russia, India, and China. Those are major players in this process. And they are going to really change how our whole world is in the next 20, 30 years. The key issues are food, water, energy, and energy is really key in this. Energy per capita is strongly coupled to the economy. You see plots of energy per capita in function of GDP. Its price of energy is a major variable in how the economy evolves. And you only have to look at the price of fuel at the pump, $4.25 for gasoline or more for diesel, to know that it impacts you directly. So it's important, and it's important over the globe.